Hi, this is Lab 3 Oscillations. The purpose of the lab is to observe the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring, and compare it to a computational model that demonstrates the same motion in ideal conditions. The lab also includes plotting the energy changes in the model to validate the energy principle. By ideal conditions, it refers to there being no other forces acting on the system except for the specified interactions, and the computational model assumes these ideal conditions for the experiment, and thus creates an example of how the motion should work in theory and in accordance with fundamental physics concepts. So, the system is mass, springs, and the Earth, and the surroundings is everything else, which is nothing since the Earth is included in the system. Some fundamental concepts are the energy principle, and we use the spring potential energy, kinetic energy, gravitational energy. And a note is that since Earth is included in the system and there are no surroundings in the lab, there will be no external work done on the system by its surroundings, thus making the total energy equal to zero. And we also consider Newton's second law with the velocity and position of the formulas. And these are diagrams of the system. So the experiment procedure is to download and import a video of an oscillating spring mass system onto tracker software to track the system's position at set time periods according to an axis defined in the software. And then create a computational model of the Earth of the mass's position according to the same axis defined in the tracker software, which serves as the ideal motion of the mass in ideal conditions. Then we use the computational model to compare the predicted versus actual motion of the spring mass system and analyze results. And this is the tracker video. So the initial time was 0. The delta t between each recorded position is 0.095 seconds. Initial velocity is taken from the first two positions recorded on tracker with the initial positions, and then we define g, the spring constant, and the relaxed length of the spring, which is given. This is the code for the computational model. And it's continued. So this is basically just the energy principle. And then this is the output of the computational model. So there's 3 graphs and then 1 model. And the similarities is that the motions both follow the same trajectory, which is sinusoidal, and the positions are generally increasing and decreasing within the same intervals and have the same direction of motion. And the difference is that for both the x and y directions, the position typically increases and decreases faster than what's predicted. Possible error in using the tracker software is that axis scaling might not have been accurate and the center of mass may not have been accurate due to human error. And the assumptions are also not true because in this experiment we assume that there's no external work being done on the system by the surroundings, but in reality forces other than those included in the equation, like air resistance, can be influencing the motion of the spring mass system, which is why the actual position is different than the predicted, because there are forces that we haven't considered that cause the mass's position to typically be lower than what is expected with the assumptions. For the questions for the model system, the energy principle is satisfied. As mentioned in the note, there's no work being done by the surroundings on the system, and there's no heat transfer between the systems and surroundings. So the energy principle becomes delta E equals 0. In the model, energy is conserved because the change in total energy is 0, and the plot also shows that there's no change in the total energy between the curves representing the kinetic, spring potential, and gravitational potential energies. And then from the x position data, you get that the period is about 1.7189 seconds, but with the y position data, we get about 1.523 seconds. And the discrepancies go back to the discussion about potential error and plotting on tracker, because for a mass spring system, the period of oscillation should be identical since the variables m and ks, or the spring constant, are equal, and everything else in the formula is a constant value.